Are your spectra scattered about? Do not despair. Gather them by MSC. Welcome back from the break. Savitzky-Goulet is a method used for smoothing and derivation. Let's first have a look at how this method actually performs the smoothing. In the following example, we are only performing a smoothing of the spectra. We use 7 points and a second-order polynomial smoothing function. As can be seen, this method scans through your spectra and estimates the smoothing and derivation for each point separately. There are 3 parameters which should be decided in the Savitzky-Goulet routine: the degree of derivative sought for, the number of points used in the smoothing, and the polynomial order of the smoothing function. It is important to be aware that as the degree of derivation increases, the signal-to-noise ratio decreases. This is especially the case if few points are used in the smoothing and/or high polynomial order for the smoothing function. An example for an estimate of the second-order derivative can be seen here, where 2 different numbers of smoothing points have been used. In the first case, where the number of smoothing points is 7, the resulting estimate of the derivative oscillates, while if the number of smoothing points is increased to 15, a nice and smooth derivative is estimated. As the signal-to-noise ratio decreases as a higher derivative is wanted, a larger number of smoothing points or lower-order polynomial smoothing function should be used. To our knowledge, using the second-order polynomial smoothing function both for the estimate of the first and second derivative is sufficient. Using 5 to 7 points in the smoothing for estimation of the first derivative is adequate, while it should be increased to 7 to 11 points for this estimate of the second derivative. As for Savitzky-Goulet, there are 3 parameters which should be set prior to estimating the derivative: the degree of derivative, number of points used for the smoothing, and the gap between points used in the estimating the derivative. As opposed to Savitzky-Goulet, a first-order smoothing function is always used. After the smoothing of the spectrum, the estimate of the derivative is then calculated based on this smoothed spectrum. This is performed very much like finite difference estimate of the derivative, but with the possibility of using a gap size which is different from 1.
Pre-processing of NIR, how may I be of assistance?
In Norris-Williams derivation, what is the gap for? Can't you just always use a gap size of 1?
The best way to dig into this excellent question is to look at what actually is happening during smoothing and the subsequent derivation. If the smoothing is performed using 5 points, 2 points at each side of the point to be smooth are used for averaging. If then we use a gap size of 1, it means that we simply find the difference between these 2 adjacent measurement points in the smoothed spectrum, right?
Yeah.
These 2 points, however, are calculated as the average of 5 points, 2 points on each side. The estimate of the derivative will therefore simply be the difference between 2 points, 5 measurement points apart, divided by 5. This means that the only effect the smoothing step has had is scaling down the estimate of the derivative in comparison to using the raw spectrum. If the gap size is larger than 1, the smoothing will have an effect.
As for Savitzky-Goulet, the number of points used in the smoothing should be between 5 and 9 for the first derivative and 7 to 11 for the second derivative. In general, a gap size of 3 seems to give good estimates of the derivative. To finish off the discussion of the derivatives, we would like to add some comments on the Norris-Williams method. In general, this method is not so mathematically founded as the more sophisticated Savitzky-Goulet. Especially the use of the gap size cannot readily be defended from a mathematical point of view, as such a gap normally would require a frequency signal. However, as can be seen from the many applications of this technique on NIR, it seems to work nicely. Probably this is due to the smooth nature of the NIR spectra. We would anyway like to recommend the users out there to use Savitzky-Goulet for the estimate of the derivatives. We can sum it all up by stating as follows: if you have a set of NIR spectra you would like to use for regression or classification, running them through the following pre-processing methods should result in a near to optimal model in the end. MSC with the following settings: first order reference correction and second order wavelength correction, only first order reference correction, commonly known as basic MSC, only second order wavelength correction, commonly known as D-trend. Furthermore, we would like to suggest running Savitzky-Goulet with a second order polynomial smoothing function It's 7-point smoothing for the first derivative and 9-point smoothing for the second derivative. Thank you for viewing this e-poster.